Hi, welcome to online tutorial videos from JCB RLS. For more information and to download the model of this video, you can visit us at www.jcbrlabs.org. In this video, we will talk about DC to DC converter, and specifically we will be designing and simulating a buck converter, which is a kind of a step down converter in this video. Further, we also provide online training, online coaching classes, help in technical assignments. We also do freelance projects based on Matlab, embedded system, machine learning, data science, Python, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrlabs.org, or you can also mail us at jcbrlabs@gmail.com. Okay, so let's start. As we discussed, we will be talking about this DC to DC converter. Okay, DC to DC converter. So what are DC to DC converter? These are simple electronic circuit which convert one level or say a DC voltage to different levels of DC voltage, right? Let's say we have a DC to DC converter here, and we have a input supply, or let's say battery of 20 volt, but at the output side, let's say we want a different values. Let's say we want 10 volt. Okay, so it will be a step down converter, or we want, let's say, 30 volt at the output. That could be the step up converter. Okay, so if there is any such requirement, then we use DC to DC converter. So they just use pulse width modulation techniques to convert these values. So when we talk about the types of this converter, so they are basically two types: isolated, and another one is the non-isolated type. Right, so in non-isolated type, they are buck converter, boost converter, buck boost converter, cuck converter, zeta converter, and SAPIC converter. Similarly, in isolated type, they are flyback converter, forward converter, single-ended two transistor forward converter, phase shift, full pitch converter. So there are wide varieties of converters available, right? Similarly, we talk about in terms of the output voltage. So there are two categories, like step down converter. Basically there are three categories, and then there are specifically which are used for step up converter. That means the output voltage will be greater than the input voltage. In this step down, output voltage will be less than the input voltage. And there is another series that is step down or up converter, right? Step up or step down. That means this type of converter can be used as any kind, like they can be used as a step up, or they can be used as a step down converter. Okay, so in this video we are talking about this step down converter, and there is a category of one kind, and that is known as the buck converter. So we will be talking about this buck converter only. Okay, so if we talk about which kind of buck converter is, it is a step down converter and non-isolated type. Okay, so now let's move forward. Let's have a circuit diagram of it. So circuit diagram is very easy. So circuit diagram is very easy. We have a power supply here which we want to use. Let's say it is an input voltage, and then we have a transistor. Okay, so instead of this transistor, this is mainly a switch. So transistor is acting as a switch, so we can use any transistor. And then we have an inductor, and at the output we have a capacitor, and then we have a diode here. So this diode is a freewheeling diode, and at the output we have a load resistance. So the output of this buck converter is very much dependent on this load resistance, and we'll be seeing within a minute. It is capacitor, it is L, it is D, it is any transistor T. So the output voltage will be this much, plus minus V out, and this will be output current. The current flowing through the inductor is IL. Okay, so what we do, we simply apply a pulse train here, and the duty cycle of this pulse train keeps on changing, and depending on this duty cycle, this output voltage varies, right? So when there is a on, this transistor is on, so this input voltage applied to the inductor, and the inductor gets charged up, right? And when there is a off, this diode will turn on, and then this inductor will discharge through this one. Okay, so there is some high and low amount of current which is flowing through the inductor. That means there are ripples in the current. Similarly, there are ripples in the output voltage. So here this C, because this voltage is fluctuating, so this C acts as a filter. We talk about this C acts as a filter. So the value of C and L can be decided based on the respective formula. Okay, so now we will talk about the working of this one, or some governing equations for finding the different values of this L and C. Now we can assume that whatever clock signal we are applying, where it has a frequency of f. So this f will decide the value of this L and C. Okay, so when we talk about working, so in general term, that means if we talk about input and output power, we talk about, so power input is equals to the power output if we talk about all the ideal cases. So that means if input voltage is greater than output voltage, because it is a step down converter, so it implies like I out will be greater than the input current. Okay, only then this power condition can hold. This is the input current. Now this buck converter operates in two modes, so we are not going into deep down of these equations because that is out of scope of this video. So if we talk about two modes, so there are two modes in which this buck converter works, and that is continuous mode. So in continuous mode, what happens, this inductor current IL never touches zero. So it decreases, but it never becomes zero. So in this continuous mode, this particular relation holds good. That means the output voltage is equals to D times of the Vn. So what is D? D is the duty cycle of the pulse train. Okay, so we can say D is V out by Vn. So I am sure you all are familiar with the duty cycle. Similarly, in the continuous mode of operation, the value of L and C can be estimated as well. Okay, so the value of L can be given by, this L is given by V in minus V out divided by delta IL into D times of T. So instead of T we could have F. So this is T is nothing but just the inverse of the frequency, and the value of C, as we said, it depends on the ripple voltage, how much ripples we want in the output. So this is 1 minus T divided by 8 times of L del V out over V out into F square. Okay, So this is the, because this value of C is based on the ripples which we want in the output. So this formula specify the minimum value of C. That means if we want rest ripple, we can have any value of C which is greater than C minimum. That means C could be greater than or equals to C minimum. But this much of C is required if we want a specific values of a specific amount of ripples in the output, and we will seeing in the simulation as well. So this is for the continuous mode. As we say in continuous mode, this this relation holds good. So our main requirement remains like this operation or this buck converter keep working in the continuous mode only. Okay. So now in the discontinuous mode, another is the discontinuous mode. So in discontinuous mode, the output voltage doesn't hold that relation we just discussed. So in discontinuous mode, IL becomes 0 for some time, right? That means it becomes like this. IL, it's starting and then decreasing and then 0, then again starting and becoming 0, and so on. Okay, so in this the output voltage become the, it is not directly related to different values of duty, directly not related to duty cycle, and then it becomes d2L by I square over d square Vn into t plus 1. Okay, so if we, it depends on all these values, output current and everything. So if we keep on increasing the resistance, then the output will be equals to the input voltage as well. So there is a limitation, there is a limit, or we can say boundary condition for continuous mode. So boundary condition for continuous mode is decided by the formula which is related to like D equals to 1 minus 2L by RT. Okay, so that means if this is the minimum value of duty cycle which is required to operate this particular thing into the continuous mode, so this duty cycle must be greater than 1 minus 2L by RT. So this is values depending when we have specific R and specific L, right? Specified R. So we can also write this particular equation in terms of resistance. So resistance means all these are the load resistance RL. So this RL could be defined, suppose if we have a specified value of L, let's say we have defined L, so this RL should not be greater than this maximum value of this RL can be decided by this RL max equals to twice of L divided by 1 minus D into T. That means we can put a limitation on the load resistance for a specific value of L. If RL goes to beyond this RL max, then our converter will become will go into the discontinuous mode. Then the output voltage will no longer hold the relation of duty cycle of the input voltage. Okay, so we will also see through the simulation. So this is the case in which suppose we have designed this buck converter with the specific value of L and C, and then we have to provide like this much of load resistance maximum it can carry for continuous mode of operation. Otherwise, if we go beyond that particular load resistance, the buck converter may not work well. Okay, output voltage may not work well. Okay, so now let's design by taking an example. So example is, let's say we have a input voltage of 30 volt, and then we have output voltage of 12 volt, and let's say maximum power which we want to deliver to the load is 120 watt, and operating frequency is 500 kilohertz. So this is the frequency at which which is applied on the switch. And the inductor ripple that means del IL, we want it to be 30% of IL max. That means maximum value of inductor. And the output voltage ripple we want within the range of 200 millivolt. And there we can also apply in some cases. So okay, now from here we can find different values. So let's say first divide D. So D equals to V out by V in, so it comes out to be 0.4. and then I out, maximum output current which can go, is obviously P divided by V out, and it comes out to be 10 ampere. So we can find out IL, del IL, which is 0.3 to the maximum value of I out. So del IL is 3 ampere, and based on this del IL we can find the value of L, which is V in minus V out divided by del IL into D into T. So it comes out to nearly 4.8 microhenry. So this L should be greater than or equals to this 4 microhenry, and we can find the value of C. Value of C can be found from this particular formula. So we can say the minimum value of C, right, it comes out to be 3.75 microfarad. Now once we have divided this L, now we can find the value of R, or RL max, maximum load resistance, which we can apply on it, and it comes out to be 8 ohm. That means if we increase the resistance beyond 8 ohm, the output voltage will not be output voltage will not hold at 12 volt. Okay, it will go beyond that. Okay, so these are the values. This is how we can estimate the different values of this buck converter, L, C, and everything. Now let's for the simulation part of it, and we will test each and everything in the simulation as well. Okay, so open Matlab, and in Matlab open Simulink. In Simulink, let's create a new model, and first task we'll do is to save this particular model. We'll save it on desktop. Let's say buck converter, and save it. Okay, we need a voltage source. So there are two type of categories: power system models and the SimScape model. So this power system blocks don't connect with the SimScape mode, so you have to be careful about that. So all the models, all the blocks which will be taking from the Simulink library these will be from power system blocks, sim power systems we are taking. So we have our DC voltage source, and then we need a switch, so we will take idle switch. We need RLC branch, a series RLC branch, and we need 3 of that. From here we will convert, and then we need a diode. Okay, so here it is, the diode, and we need a voltage measurement. This voltage measurement, we need a current measurement as well. Okay. Now we need a scope, a sink, In order to show the values, we will use this one to display the value in numerical form, and we need a pulse generator. Okay, so now let's connect these things together. Okay, let's zoom it up a little bit. Okay, so we have a voltage source. This voltage source will be applied here. We need to flip this diode. Okay, so change it to, okay, we need 3 of these. Change this one to inductor only, and the value of this is I think 4.8 microhenry. So 4.8 microhenry, that means to the power 6. Apply, and then let's connect. We need a C, change it to L only. We need a C only here, and the value of C, minimum value of C is 3.75 microfarad. And rotate it. And then we need only resistance, and the maximum value of resistance, load resistance, comes out to be 8 ohm. Rotate and flip. Okay, change it to R only. Now we want a current measurement, so we will connect a current here, and the output of current will go here, and all these things will come together. Yeah, one thing we forget to add is power GUI. Without this, this model will not simulate. So we will put it in continuous mode only. Okay, now we'll set the parameter of pulse generator. So let's say amplitude 5, period. So frequency was 500 kilohertz. So period comes out to be 1 divided by 500 kilohertz. So it is 0.000002. Apply, and then pulse width is 40% duty cycle. Okay, this will connect here. Let's configure the scope. We need 2 current and voltage measurements, so we need 2 axes, and in history we unlimit this. Apply, and then okay. We will be measuring the current, voltage. Okay. So one is connected to this, and another is connected to the current, and here we will be measuring the voltage on display. Okay, so and change the DC voltage source. We need a 30 volt. Okay, let's save it. It seems like everything fine. Now we'll simulate it for 0.01 second only, because if we start simulating it for 10 seconds, it will take a lot of time because there's a high frequency there. Okay, let's simulate it. Okay, so if everything goes fine, I think yes, it is working. Yes, you can see the output is limited to 11.8, very near to near about 12 volt. And if we check the scope and make auto scale, so you will see the output voltage goes slightly momentary up, and then it limits to 12 volt only. And now if we look at the ripples which are appearing here, so ripples are within the range of this 200 millivolt. Look, it is going up to 11.95, and here it is near about 11.75. So ripples are within the limit of 200 millivolt. That's why we said that is the minimum value of C which is required for that amount of ripple. So if we increase the value of C, let's say we increase the value of C to 10 microfarad, okay, so the ripple will reduce. There will be no effect on voltage, but there will be a reduction in the ripples and the output voltage. Okay? So if you further see, now ripples are within 60 millivolt range only. Okay, maximum is near about 11.86 and minimum is near about 11.8. Okay, so that formula which we derive, this C, this provide the minimum value of C which is required for the minimum amount of ripples. Okay. Now let's change it to a previous value, that was 3.75, and now let's see what happens to the R, because that was a maximum allowable limit of the resistance. Let's say we increase the value of R to 20 ohm. Let's see what happens. Output will no longer hold the relation, and now we are not getting the exact 12 volt, we are now getting 16 volt. And even if we try to make it an open circuit voltage, right, now it is open circuit voltage, now output will be equal to the input voltage, 30 volt. That is because this capacitor will charge up and it is not going down, so we are getting a constant 30 volt output. Okay, so that is the role of this R, or we can say the load resistance, because once we have designed this L and C, now we have to put the limitation on this load resistance, or cap, like maximum, what could be the maximum value of this load resistance. Okay, so this is very important to understand, because many people get confused when we try to make it open circuit. So if we let's say right now our value of R is 20 ohm. Now we can do one thing. Remember, if R is increased, then we can change this value of day, that means duty cycle, in order to come back into the, in order to drag back this converter into a continuous mode. So let's change, if we can do that, if we reduce this duty cycle, let's say to 30%, let's say what happens. Yes, the voltage is reducing, right? So it is again coming into the continuous mode, and we can, let's say 25% of duty cycle. Yes, it is again giving the same required voltage at the different value of R. So from here it is evident, like if we want to increase the value of resistance, we have to decrease the value of this pulse generator, or this means duty cycle. That means ultimately what is happening, from this duty cycle we are changing the equivalent circuit of this buck converter. That means the impedance, internal impedance of this buck converter is dependent on the duty cycle, and by changing this duty cycle we can change the impedance offered by this buck converter to the source. Okay, we will discuss this particular concept in some other video, but I hope you understand how to simulate this buck converter and how to make it work in different conditions, and what are the several conditions which are required to make this proper, or to make this model work proper. So let's change back value R to its original values, 8 ohm, and to the 40% of this duty cycle. Okay, so let's run it last time. Yeah, so these are the design equations, like how to find the value of V out, L, C, and then maximum value of RL, allowable maximum resistance, load resistance, and the value of D. So one question is obvious to come into your mind. We can apply let's say a controller in order to get the constant voltage, and how we can do that. Let's say this is our buck converter, and this is the output voltage. So what can we do is we can fed this output voltage to a PI controller, or let's say to PID, right? And from here the output of this PID goes to the duty cycle of this buck converter. So what actually it is doing, it is trying to change the duty cycle to make here it is V reference, to make this output voltage equals to the reference voltage. So let's say if we have changed to 12 volts, so this output voltage should be equals to 12 volt. And if there is a change in the resistance, so output is changing, this PID will change the duty cycle of the buck converter to again drag back this output voltage to the 12 volt. So this is how we can create a closed loop. It is an example of closed loop control of buck converter. Okay, so I hope you like this video and you understand a lot about the designing and several other aspects of the buck converter. So that's it for this video, and further if you have any doubt, any suggestion, any queries, then you can let us know by commenting below this video. And further, we also provide training, online coaching classes, help in technical assignments. We also do freelance project based on Matlab, embedded system, machine learning, data science, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrlabs.org, or you can also mail us at jcbrlabs@gmail.com. Okay, so that's it for this video. Thank you.